Hello and welcome to Toddcast number 59. Sort of winding down the alcohol, aldehyde, ketone chapter, but a few more things to cover. And these, again, have a very significant bio application because there are so many alcohols and ketones and aldehydes in biological molecules. We touched on these without naming them when we talked about protecting groups. But you can convert a species with two bonds to O into another species with two bonds to O and yet another species with two bonds to O by simply moving H's around and O's around, bonds to O and bonds to H's around. And those compounds are to be known as acetals, hemiacetals, ketals, hemiketals, aldehydes, and ketones. And so we're going to look at the correlation between these and then bring up just briefly how they have biosignificance. But with that in mind, I want to consider what the various compounds are because it becomes pretty important nomenclature-wise to know what they are so that when you see these later on, especially in sugar chemistry, you'll be more well-versed in them. Okay, so first off, a ketone, carbonyl with two R groups, don't have to be the exact same R groups. They may be, may not be. But if you treat this compound with excess ROH in the presence of base, you get a species known as a hemiketal. Hemi meaning halfway. So let's count the bonds to O. Carbon has one, two bonds to O. Carbon has one, two bonds to O. The difference here is that in the first structure, the ketone, both bonds to O are to the same O, so a sigma and a pi, whereas in the case of the hemiketal, they are both sigma bonds, but to two separate oxygens. Okay, so one of the H's, or one of the O's, excuse me, has an H, one of the O's has an R. Now, therein lies the difference between what will be called a hemiketal and a ketal. So just as there is an H in hemi, there is an H in the hemiketal. And so we'll talk about how you go a little bit further with that one. Um, and well, we'll talk about it right now. If I do excess uh, alcohol, but I now do it in the presence of an acid, the acid allows the ketone to react one step further. So the difference is with base, the OH minus can attack, kick that up, and it's sort of stuck. It's just going to stay in that state, or the OR minus would come in and kick in. But if you're an acid, what you can do is take this species here, the hemiketal, and we're going to learn how in, I guess, very short amount of time here. If you protonate this OH, so if it were to pick up an H plus, that becomes water. Water is a good leaving group because water can leave, a second ROH can go on. And so I don't want to mess up that mechanism up top, but go back to just if you do it in base, you can only go to hemi. So if you have OH, then you get an H still on there. So hemiketal, whereas if you do it in acid, you can go all the way to the full ketal. So ketal is OROR. So I'm going to refer to it incorrectly, but still okay for me. A double ether, meaning you have an OR and another OR on a carbon. Okay, so ethers are very stable. Ketals, like ethers, not quite as stable, but still relatively stable. That's why we use it as a protecting group. So if I go back to the Bart-Simpson protecting group, I have a carbonyl. As long as these are R groups, then lo and behold, we have a ketal protecting group. Okay, so perfect. So I've seen it, I just didn't know what it was called back then. Okay, so OR, OR, ketal, OR and OH, hemiketal. Okay, so we've taken care of the ketal and then added in the hemi, and we've dealt with the ketone to do it. The only difference, the thing we now need to look at to be complete, aldehydes and acetals go together. So just like we saw with basic conditions with a ketone, it only went halfway, hemi. Same thing with an aldehyde. You get a hemiacetal. So if there's an H in the name, there's still an H on one of the oxygens. Whereas if you do it in acid, you go all the way. Okay, fun fact, you can go backwards in every single one of these reactions by adding H2O, no H minus, H2O, H plus, H2O, H minus, H2O, H plus. So the reversible reactions. So if I wrote it more like an equilibrium, then I could do the following. So for the first one, apologize because this is going to be a little messy. So let me get rid of these reagents and simply say that in the presence of a base catalyst, you can get an equilibrium where if you react an R, O, H, I'm going to put a prime on it so it works out. And we'll ketone, you can get the hemi, ketal, and water. Add water, you push it back this way. Add alcohol, you push it this way. So if I want to make a hemiketal or a ketal, then I need to do it under dry conditions, no water. So I alcohol and whatever the catalyst is, base or acid. If I want to get rid of the hemiketal or the ketal, then I need to add a bunch of water in there to push the reaction in the reverse direction. So water gets rid of protecting groups. Alcohols are used to form a protecting group. Okay, so this is just straight nomenclature. The reason this becomes so important in bio is our sugar linkages end up being either acetal, hemiacetal, ketal, or hemiketal linkages, depending what the sugars are, and they behave very differently. So if it's hemi versus a full, keep in mind full are protected. So protecting groups, Bart Simpson is a full ketal or a full acetal. And so if you have it protected, it can't react. Same thing. Hemiacetals are highly reactive forms of the sugar, whereas acetal form not as reactive. Okay, so important to know the mechanism. So I'm going to go through this mechanism really slowly, but I want you to absorb not this specific mechanism, but the reality that what I'm doing here can be used in several acid or base catalyzed mechanisms. So this will be under acidic conditions, but I want to do that same reaction did to form the Bart-Simpson protecting group. Want to emphasize that this is like ROH except two OHs on it. And so if I added water, I'll push it back to the reactants. If I remove water or I add the diol, I can push it forward to the ketal. And so it's ketal because it came from a ketone. And it went all the way, there's no H on it. Okay, so the mechanism to go all the way to the full ketal or the full acetal, you must do it under acidic conditions. Base, you only go halfway with base. You only get to the hemi. But with acid, you go all the way. So acid catalyst, so I'm going to put an acid below the arrow, and I'm going to form a ketal. The pathway, the mechanism. Because I use an acid catalyst, catalysts go on in the first step and are removed in the last step. So I know that my first step is going to be protonate and my last step is going to be deprotonate. So this is where I want you to just absorb this concept because it's pretty straightforward. We've already done it, but it becomes kind of revolutionary when you finally realize how powerful it is. So when you add a catalyst, it goes on in the beginning, regenerated in the end. So protonate's your first step, deprotonate's last. When you protonate something, you make it more positive. That makes it more of a leaving group than a nucleophile. So bonds have a tendency to break in protonated or positively charged molecules. Once a molecule has undergone a breakage, or once one of the bonds are broken, it leaves room for something to come in, a nucleophile, whatever that nucleophile ends up being. And so we're going to protonate to make a good leaving group. Leaving group is going to leave, meaning we're going to break a bond. Then the nucleophile, like an SN1, is going to come in, and then it'll deprotonate. The only thing that sort of derails this very common mechanism is rearrangement. So in the absence of rearrangement, which we don't see in the ketal ketone or acetal aldehyde relationships, you don't have to worry about rearrangement in those. So we'll just say these steps. So sequentially, first step, protonate. The most basic site will actually be the carbonyl because it has a delta minus. The alcohol OHs also have a slight delta minus, but not as much as the one with the pi bond that can break and put a full negative charge on there. These are just by inductive effect. So protonate, first step. So protonate at the O. So now you have an O that's unstable. It's positive charge in 3 bonds. And so next step has to be a break. You break the weakest bond. OH could be the weakest, but pi bonds end up being the weakest. So the pi bond's going to break. And notice that it's a double-headed arrow because this is a resonance structure. It is not an actual new molecule. So if all we've done is move pi electrons around, it is resonance. But protonate, break, so make. Can't react with itself, so that's where this compound is going to come in. Lone pair on the O is going to attack the positive carbon. Doesn't matter which side I choose, OH or OH, it's all going to be the same, but a lone pair attacks. So I now have a water molecule, or I should say, I now have this O bonded there. It's protonated like I protonate water to make it a good leaving group. But this time, I don't want to make it a good leaving group. I want to make the other one a leaving group. So I'm going to have to deprotonate here. So I'll do that. And so my steps are protonate, make it a good leaving group. So bond breaks. Once it breaks, there's an opening, carbocation, nucleophile attacks, make a new bond, and then deprotonate. I should specify that the solvent's going to take it off here, but I never specified a solvent. So for all we know, this compound could take it off, or this compound could take it off. So this H coming off could very well be the first H in another step. So I am not the same, I guess the level of stickler that some chem professors are in terms of it has to be picked up by a solvent. It is true, you can't have just free H plus around there, but it's kind of absurd to say we know exactly what picks it up. So I'm kind of somewhere between yeah, it can't be a free H plus flying off by itself, but I don't know what it's bonded to, so that's the best representation I'm going to put there. So protonate, break, make, deprotonate. So let's inventory. We have the 2 R's from the original ketone, check. 2 bonds O, 2 bonds O. This is an OR, but this one is an OH. So we didn't get all the way to the ketal, we're at the hemiketal. So 4 steps, protonate, break, make, deprotonate, got me to the hemi. So 4 more steps are going to get me to the ketal. And guess what those 4 steps are going to be? Exact same thing. Protonate, break, make, deprotonate. So now we don't have a carbonyl here, so we have to figure out where the best spot to protonate is. Could be here, could be here, could be here. Reality is this is maybe the most basic. So this is where my earlier statement that it's going to protonate the most basic site. When there's a distinct difference, yes, but when they're roughly equal, it can protonate any of those. But if it protonates here, it's just going backwards. And if it protonates here or here, then it's free to have some attack. It ends up, this is probably your better spot to protonate because these lone pairs can come and kick it out, share the electron density and make it a little more negative. So protonate, you now have a leaving group, make. Another molecule could come through the solution and attack and kick that water out, or it can come in internally and kick it out. Keep in mind that it's going to leave first because under acidic conditions, you make a good leaving group. Water is going to leave, and the chance of another molecule coming in and attacking it versus attacking itself, if the ring size is viable, it will attack itself. And a 1, 2, 3, 4, 5-membered ring is reasonable. So you're going to have intramolecular make. So it's going to form a bond. So protonate, a good leaving group leaves, nucleophile attacks, and last step. So let's see, protonate, break, make, deprotonate, protonate, break, make. Yep, deprotonate's my last step. Only have room for a little bit. going to come off, and I now have my compound. I have two R's and then the Bart-Simpson part. It works. It's actually amazingly simple. Um, Simple is probably the wrong word. Amazingly systematic. You just have to recognize what happens in each of these steps. You will have to know this mechanism inside and out for your biochem, for your OChem, just very, very common mechanism. Protonate to make it a good leaving group. You break a bond, you make a bond, you deprotonate to make it neutral. If it's what you want, great. If it's not, then you start all over. Protonate, make a good leaving group leaves, so you break a bond, tax to make a bond, and deprotonate. Okay, so if you have a ketone and you want to protect it, what do you convert it to? Well, Bart-Simpson, basically asking what is Bart-Simpson? Because it's a ketone, it's got to be either a ketal or hemiketal. So I can get rid of these because those come from aldehydes. And protected is the full ketal. So a protected group, stable under basic conditions. So you add a Grignard reagent or something, it won't react. Grignard being basic. So under acidic conditions, you can't really protect, but under basic conditions, I can protect. So aldehydes are protected as acetals. Ketones are protected as ketals. So best answer for this question, because we're talking about a ketone, is a ketal. Okay, so ketals are stable under basic conditions, while hemiketals are not. Um, Thus, ketals are better protecting groups than hemiketals because they don't react. Okay, so I'm feeling pretty good about this. I want to transition. I want to remove a protecting group. And so just want to revisit something we mentioned. From alcohols, so once you have that group on the silicon, so again, you had a chlorine, the O displaced the chlorine, F is going to displace the O. So I'm putting HF. I want you to recognize F minus as the active ingredient. But if you do any textbook problems, even one of the homeworks I mess with you, you're going to see an F at the end of something. So it might be, let's say, TBAF, tetrabutyl amino ammonium fluoride. Then, as long as it has an F, just recognize the F. So when you see the F? What the F? Right here, this one? F will work. Okay, so you're going to get the alcohol back and then the fluorine on the silicon. From aldehydes and ketones, so for instance, this one, I can protonate here, undo the Grignard salt, but I can also, when I do that, run this reaction backwards. Protonate, break, make, deprotonate, and then water comes in, protonate, break, make, deprotonate, and you're back to what you want. So a quick and easy way is to recognize water is going on. So I got rid of the water I had before. If I put in that arrangement, I now have, if I look at this, an O with H and H, and I have that group over there, and I have two bonds to the O. So my water is going to go back on. So water and acid will get rid of your protecting group. So note the O and the two H's become the O and the two H's. So perfect. If I use a strong acid, the problem with that, you can get elimination, and with elimination, you run the risk of getting rearrangement. So carbocation, and I should say not just elimination, but in E1, strong acid, E1 elimination, protonate here, but protonate at the same time, OH leaves, H moves around, ends up in a conjugated position. So you can get a so-called alpha beta unsaturated ketone. So double bonds in resonance with a carbonyl, a little more stable. So if I want to remove a protecting group, I want to use as mild a condition as I can get away with. So again, barely get things done, aim low. So if I use too strong an acid, I'm going to get side reactions that I don't want. If I don't use a strong enough reagent, so if I just use water, it won't react. So I need to add just enough acid in there to remove it, but not so much that I start getting other reactions. Okay, so this covers protecting groups, in particular ketals and acetals. Hopefully it seems okay. I again want to emphasize this will pop up at some point when you do carbohydrate chemistry. So with that in mind, I will stop the recording. So I will see you the next podcast. Bye.